We talked already about the converse. It's when you switch the hypothesis and the conclusion from the original implication. Inverse is one we don't use very often, but it has a name, so I might as well share it. It's when you keep the order P and Q, but you just negate each of P and Q. The contrapositive will be a very useful one that we'll talk about later, and it's created from the original implication by not only switching the order of the P and Q, but also negating both of them. Let's consider the following implication. This is an example from our textbook, A Spiral Workbook for Discrete Mathematics by Harris Kwong. X equals 1 implies x squared equals 1. We could also read that as if x equals 1, then x squared equals 1. We're going to simultaneously consider the logical structure of this and the truth value of each of the pieces and how that reflects on the truth value of the entire statement. If x equals 1, then we have to have that x squared equals 1. If we know that x equals 1, that's enough for us to get that x squared is equal to 1. Think about it. If we just square both sides of this given equation, we get exactly that second equation. We have a valid algebraic procedure we can do to go from our starting statement to our ending statement. And remember, the hypothesis is what we call the sufficient condition. So if x equals 1, there's no way that, for example, x squared can equal 2. It just doesn't make sense. If we're assuming x equals 1, x squared has no choice but to be 1. Think about it the other way, though. If x squared equals 1 is all we know, we cannot guarantee that x equals 1. X squared equals 1 is not sufficient. It's not enough for us to conclude that x equals 1 because it's possible for x to be negative 1 if we're just assuming x squared equals 1. That tells us x squared equals 1 is a necessary condition for x equals 1. Let's work on this hands-on exercise together. We're going to write these two statements in the form if P, then Q. The important thing when we're translating from words to symbols is to specify what your propositional variables will stand for. And the propositional variables we use most often are P and Q. So for part A, for x squared greater than 1, it is sufficient that x is greater than 1. Okay, which is the thing that's sufficient? What does this sentence grammatically say is the sufficient thing? Okay, let's see. It is sufficient that x is greater than 1. So x is greater than 1 is sufficient for x squared greater than 1 to happen. So the sufficient thing is x is greater than 1. I'm doing a little scratch work here, not quite at the final answer yet. X is greater than 1 is sufficient for x squared greater than 1. I rewrote this sentence in a way that helps me more easily determine what goes where. Now remember, if P then Q, this is the sufficient condition and this is the necessary condition. That tells me that if I assume P is the statement x is greater than 1, Q is the statement x squared is greater than 1, my final answer is if P then Q is what part A says. Again, right now we're not trying to figure out whether or not this is true or false. we're trying to just analyze the structure of it and apply what we know about if-then statements and the words that signal us that something is an if-then statement to write it in symbols. Let's go on to part B. For x squared greater than 1, it is necessary that x is greater than 1. All right, so reasoning out loud again. What's the necessary thing? So x is greater than 1 is the necessary thing. X squared is greater than 1 is necessary for x squared is greater than 1. X is greater than 1 is necessary for x squared greater than 1. We're not thinking about what's true or what's not true. We're just thinking about the word necessary and how it applies to this situation. Remember, Q, the conclusion, is the necessary one. That tells us that the Q is actually the x is greater than 1 part. Using this same definition of what P and Q are, we have if Q, then P as our final answer for part B, translating it into symbols. What did we do in this video? We talked about treating implications logically like promises, because that's the convention in math and computer science, because you can get very philosophical and not decide what implications are logically, what the truth table should be, but we have very useful conventions in math and computer science that help us do a lot of stuff, so that's why it's a convention. We learned some new symbols and words that signal whether something is an implication, also known as an if-then statement, and we talked about some other ways we can create new implications from a given one. And we called them the converse, inverse, and contrapositive. Notice the converse will not necessarily always be true if the original implication is true. We saw that with the example involving prime numbers. And I mentioned contrapositive is going to be a very important form that we'll do in more detail later.